There's less people than on Friday. Is it because? Hi, Lisa.
Hi.
I'm complaining to my colleagues that I fear students of this year class. They are too smart. And I also complain like they do not fear homeworks and not seeking to escape it, as it typically happens. Mm-hmm. If you go with this pace, I need to squeeze 2 lectures in one and give more material. Okay, take your time. You're missing Morgan? Do you see anything ready for submission at his table? So how are you looking at the opportunity to repeat the exercise of Friday? Of self-grading. Then I don't know, those who are not participating may miss a little of fun. And I'm not sure Young-Yu should be here as well.
I've seen him today, but I don't know if that means that he might have tried to
Okay. Those who participate in grading are getting extra point, and those who mandate me to grade their works do not get extra points. I think it is fair. Okay.
Good.
Okay. This is what we do coming Monday, right? And there will be no lecture on Wednesday, but there will be lab on Wednesday night. I'll send folder this one. But no lecture. Just take time easy on Wednesday night.
Okay.
Main thing is movies, so it will be probably only one subject and questions and answers section. So here is the grading schedule, right? So the mandatory points should total to 100, and the extra credit, let's say 40.
Sounds great.
But getting 100 is a guarantee, so it's like safety cushion. Yeah, because for me it was challenging to take the extra credit. Huh? So number one, you need to do commutation, right? And I think we did it in class. So it's 10 points, and just by applying the rule of differentiation and subtracting, one can get that swapping of the order of derivative and position applied to any function. One is getting constant, and if we multiply derivative by the minus I h bar, then derivative becomes operator of momentum, and then there is a relation that one can find in textbooks. So commutator of position and momentum minus I h bar. So what we do, the swap of the order of two operators is denoted as rectangular brackets and comma. Morgan, do you have homework? Number 3, ready?
I thought October 1st was Wednesday.
No, it's today.
Yeah, I was looking at the date wrong. I don't.
You try your best. Oh, close your eyes and do this, please.
No, but yeah.
Oh, okay.
Okay, so done with number 1, right? Number 2, it's basically copy pasting from the notes, right? So you tell that future is eigenfunction accumulation of phase with eigenenergy and expansion coefficients, and expansion coefficients is integral of overlap of the past psi at t equals 0 and one of the eigenfunctions. 10 points. Number 3, which is the highest number of points of all. So please give me a little sign if it was a challenge when you did it. Okay, did you like the comment that I sent last night? Did it make it clear?
I was confused on so when you're doing the side, how do you do the psi star of something that doesn't have an imaginary?
Psi star of something that doesn't have imaginary is psi itself.
Okay, so it's just psi squared?
Right, correct.
Oh.
So
That would have
the prescription is very deterministic, like swap sign in front of any imaginary unit. If expression doesn't have imaginary unit, then doesn't swap any
because
signs.
then I just used something from the notes, and I think that I got a little confused.
So the letter N is okay as normalization, but in the notes I suggested you to use letter P for probability. So if you take wave function squared or psi star times psi and integrate, it should equal 1 if the wave function is good. If it is not equal 1, one needs to do anything we can to achieve this, right? So, yeah, I should do my homework better and type it in nice equations. So, is it in view? Okay. How do we arrange? Oh, Morgan will grade your homework. Oh, it's a secret. Someone unknown will grade your homework. Sorry.
I feel like it doesn't really matter.
Yeah.
Like,
Well,
we're okay without.
I don't know. Well, we are trying to. Oh, I pasted the on the wrong place. He placed homework for Dr. Cuban, and I covered it and I left the name. Well, I don't know in this year how you are sensitive, but I'll try to do some measures because who knows, maybe you do not want to disclose your personality. Not everyone has submitted homework, so but just enjoy. You did 2 gradings last time, so it's fair. It's your little vacation. So just psi squared, and if it is exponentials times exponential, it's just factor 2, right? And then one can swap the change the variables, right? So shift along x-axis and make a factor, and then the as a price for the substitution will be divided by square root of 2 outside, and then it is a Gaussian integral, right? Which is square root of pi. And then if one which is not good because integral of psi squared should be 1. So by now the initial wave function is bad. It should be good, and we will make it good by tweaking the value of n, which is normalization constant, in such way that integral of psi squared will be equal 1. So if you go from here to there, so if you mandate it to be equal 1, then this is result of integration. This is unknown constant n squared, and we can solve for n squared, which will be, you will divide left and right by square root of pi over 2, and then take square root of left and right, with the square root of square root over pi. If you find mistakes in what I do, you better Huh? Yes, fourth root. So they have a, yes, I have a picture. So if this is only half of the problem number 3, right? The goal is to find expectation value of the position operator, right? So right now we this is a relatively simple exercise, but it has very important meaning. So we are approaching slowly the regime of describing the outcomes of measurements. So x here serves as operator, and here this angular brackets is expectation value. So if you do know wave function, we can find the where electron is located in average. Okay. Intuitively, if the Gaussian peak is centered at x0, we should get x0. Okay, so it will be the correct answer. And by the way, if you want to be generous, as soon as you see the answer x average equals x0, you can give it credit. But how do we get it? It's an evident problem, but we need to get through a procedure. How can we prove that multiplying this exponential square root by x and integrating will be x0? So on one hand, so here I'm practicing graphical multiplication integration. So if you have Gaussian wave function, and if we have the x, right, or shifted x, multiplication of Gaussian function and straight line that comes across the center will give the antisymmetric function, where the area under the two wings will be equal by value and opposite by sign. It will be 0, right? So do we see any paradox, or it's just an observation? Well, here it is not x, but x minus x0. So probably if we shift a variable as we did for the first part, there will be two terms, one that gets to 0 and another that will get the answer. So now we are practicing the rule, that bridge that connects abstract world of wave function, operator, and expectation value that comes as observable. Expectation value of position, operator of position, wave function square, normalization factor, dx. So we already observed in the previous slide that if we multiply exponential by the linear function that is crosses x-axis at the center of the wave function, then it will be easy integral to t, right? So we subtract and then add the same term. So one integral will be exponential times this difference, another will be exponential times x0 as a constant. And then the first integral, where exponential times difference, we graphically know that it will be 0. And the second one, it will be the exponential times constant, and it is known Gaussian integral that will that should give square root of pi, right? And if you carefully take it, then and also there is a factor 2 that we need to substitute variable 1 speed. Then this integral will get square root of pi divided by square root of 2, and these constants that appear from this purple circle will cancel the p factor that is inherited from the beginning of the line, and the answer will be x. Okay. Oh, okay. It's just the details. Should I go over, or is this order? So number 4 is just reproducing stuff from the lecture notes, making comments that bit product of the uncertainty of position and uncertainty of momentum is growing this time. And probably there was a question, can it go backwards in time? Can it shrink? If time goes backwards, if we put time axis this way, will it go? Or independent of the value of time, it will it shrink? No, it will grow independent of positive or negative time. Whether we go forward or backwards in the future, it is expected to grow. So an uncertainty principle would work even for time machine. Boundary conditions. Give me a sign if this problem was giving you a hard time. Or a little. Okay. I've got one email question, but the email question that I got last night contained correct answer. And it was the question like, isn't it? So what do we do here? We assume that we do have psi function with unknown coefficients. And so basically what we do is just application of ordinary differential equations boundary condition problem. So, and we assume that at 0 and at a certain limit, and if you put L capital or pi, it shouldn't affect the answer. Do not repeat any digits. So if we assume that at 0 and at some point in the positive side wave function is 0, these two conditions should bring restrictions to the values of these coefficients and make and convert us from the general solution to the particular solution. So this function should satisfy this condition. First, we explore this functional form at the argument equals 0, and then sine of 0 is 0, cosine of 0 is 1. And then this function becomes into algebraic equation. So b times 1 equals 0, which means that b equals 0, right? So our life is twice as easier. Cosine part is removed. Then we may want to explore at the right moment. So coefficient A, the phase, or whatever rate, frequency, and the L equals 0. So the sine equals 0 if the argument equals pi, right? Length times this unknown alpha, pi times any integer number. So alpha is pi n over L. So we solved for alpha, and now there is only unknown is this A coefficient. Doesn't look like previous problem. Or one problem before, normalization. If we assume that it is a wave function, then wave function squared, or whatever favorite question for Lisa, star, if there is no imaginary part, will be wave function squared. I do not have comment why we should export from, I didn't make comment why we should export from 0 to L, but basically if wave function ever made to 0, it will be 0 before and after, not 0 in the center. So we are interested only in the limit from 0 to L. And when we have multiplication with function squared, it will be square of this unknown coefficient, sine squared, and we take the integral, the limit.
Wait, why can't A just be any number?
Which number?
A, like capital A?
Uh-huh.
Why can't it be any number? The sign of
If we are mathematicians, it can be any number. But if we are in physical chemistry course and we bring meaning, interpretation of the wave function, there should be only one electron. So the meaning of this integral, is how many electrons are located in the space area from 0 to L. And by now, we are working only on one electron problem. So the answer should be predominantly 1. So we need to tailor such a value of a capital coefficient that the result of this integration will be equal to 1. Make sense? Or it's not quite.
I just don't know how you would, like I get the whole math thing, but I just don't know how you would intuitively be like, oh yeah, this is.
Well, it's partially my failure. I need to declare it more evidently again and again at different points, but by the end of the course, you will tell this philosophy with closed eyes. I promise. Okay? Done? I will not. It's extra credit, so I will not show the solution. And then it will give me unties my hands to do it once again as a regular. Would you please add together points and place them near the top? It doesn't matter. Just add together the points and put it in. It's a point that it is a secret. Undisclosed code. Maybe a generator. Tech support? Can you check that camera is focused on this screen? Sure. Okay, that's good. Thank you. Just pass it to me when Morgan, when you are done. So we already talked about portraits on banknotes, the money, right? Political figures, presidents, or scientists. What do people show on the postage? Like the one I have now is flowers with cacti, right? Sometimes there is a flag of the country. What else can you see on the postage? Huh?
Political meetings.
Okay, what else?
Two figures in history. Amelia Earhart.
Okay. I'm repeating this course for several years, but I still do not know a specific word that you need to teach me. So, in regular life, there are superstitions which are not based on anything. And there is a way of superstitial attempt to predict future. And it is considered not a right thing to do. Is there like no even simple? Huh? It's lower level. It's like guessing. It's not magic, but you and it was known anciently. So one of these things is when he and she, no matter which side, predicts if.
Wish.
I don't know. It's different in different cultures, but in one of the culture, you can take flower of chamomile and pull the petals, and yes, right. And depending on what will be the last one, it will be the answer. So, what is the name of this procedure?
Maybe the one thing that doesn't
Is there a name for this procedure?
No,
I don't
it's
think
just
so.
you.
No.
I
Okay.
think it's like a childhood, not rhyme, but like.
Okay.
Chance. It's like
So in Germany, they put it on the postage, and this person was so he pulls the petals from chamomiles chamomile and tells position, momentum, position, momentum.
Who would under?
yeah,
Who is this catering to?
It's the same person, like being 25 years old and 70 years old. But Werner Heisenberg was a competitor of Schrödinger, and he has alternative mathematical approach for quantum theory. So it's his idea about uncertainty of position and momentum, and it's his idea of the predicting expectation value of operator rather than spending time on Schrödinger equation. And he pointed attention that position and momentum cannot be known simultaneously, so he and in our class we put brackets here, otherwise it is too abstract. Okay. So what have we accomplished by now? Do you have this? No. So we do have ways to predict future, and keep sweeping. I will tell you if we need to work out. Predict future with evolution operator. Predict future with propagating wave function forward in time by finite differences, and time dependent Schrödinger equation solution, which is solved by this stuff that you already written down. The eigenfunction that comes from time independent Schrödinger equation, the accumulation of phase that comes from the eigenvalues of energy, and expansion coefficient, which comes from the overlap of the initial wave function and eigenstates. And then, if we follow the rule of Schrödinger, we find expectation value by overlapping the wave function, the operator of wave function, and get outcome of the measurement. The approach of Heisenberg is one needs two input pieces. Hamiltonian, same as for Schrödinger, and p value of expectation value at time 0. Then one practices this operator and puts equation of motion for the observer. So typically it's not one differential equation. Typically it's coupled to something else, but it will be a closed system of coupled differential equations. And then one finds how the expectation value depends on. So what is good, what is bad about Schrödinger and Heisenberg? So number of degrees of freedom in Schrödinger approach is almost always infinite for wave function. And for Heisenberg it is like coupled. So mathematically it's definitely more preferred. Mathematically challenge in some sense solving time independent Schrödinger equation is a main challenge. It's diagonalizing the matrix of infinite number of dimensions, which is a little challenging, but this, if you solve this problem numerically, it does have problem with guarantee. So it's a very comfortable numerical problem, even if the size is big. For Heisenberg equation of motion, it's ordinary differential equations, which are generally also not very complicated. If you solve problems mathematically, linearity is important. If we have products of operators or products of independent variables of functions. So Schrödinger picture is wrong word. I'll tell later. Schrödinger approach gives only linear equations, which is big plus from mathematical sense. The Heisenberg approach may generate nonlinear equations, which are big pain. So even there are a few equations. If you were taking differential equations, you know that for linear equations there is a guaranteed procedure to get answer, and for nonlinear there are like few recorded in the tables, and for the rest one just puts forward numerical solution with bifurcations and Lyapunov exponent when it can go one way or another way. So it's not always perfect. So there is no champion. There is it's like a tool that is good for either one or another situation. And I'm trying to improve this picture from year to year, but I'm not yet at the top of this assignment. So this course can be considered as arcade, as browse in the space of theories and models. And we can put 3 dimensions. So one dimension is principles and methods, and we have evolution operator, Schrödinger equation, Heisenberg equation function. Another axis will be realistic system, a model, or maybe unrealistic system where we apply the theories. And by now, we have only one electron in one-dimensional free space, right? And later on, we will put more and more different models to which we will apply. So it's basically a plan of a course. Like apply that and that to this, and this model. And eventually, we will get to like realistic models for quantum dots or whatever metal organic complexes. Maybe. And the third dimension is typically skipped from such classes. But it is very important. There is we do not have enough material to cover it completely, but as we go, we accumulate concepts. There is but I give an announcement. There is a big lie of quantum theory courses, which is, it's not intentional lie, but if one abridges course, then some details are skipped from the focus. And this, so to say, big lie is that if you prepare a system in the excited state, it will stay there forever. So in mathematical models that we deal with, if system is in the eigenstate, if it is eigenstate is not the lowest one but somewhere up, it will stay there forever. Which is mathematically correct, but it is this answer, this feature follows from an assumption that is not typically correct in the real life. That system is isolated, and we have all degrees of freedom at our disposal. In fact, any realistic system is more complicated, and there are additional degrees of freedom, such as like if it is a molecule, there is a solvent. If it is like quantum dot epitaxial, you put it on a solid substrate. It will be the catalyst. You put it on a substrate. Even if it is a free electron in space, it may interact with radiation and just cool down because of emitting photons. So nothing is isolated. And this is the third degree of freedom, perturbation from additional degrees of freedom. We will not have time to come over it in details, but at least conceptually, I will try to speak about it so that we can go around the picture. Definitely there is no time to accomplish my plans for this lecture 14, but I will just chop whatever time runs out and continue in private. So, the goal is to predict expectation value of position of our favorite Gaussian wave packet as function of time. And intuitively, it should either stay still or propagate. Do you know the game Sea Battle? Yes. Were you playing it? Okay. Nice, because they were coherently. It couldn't be notes of the lecture because one sign one person, then another sign another person, and then one.
No,
two.
that was Hangman.
Huh?
That was
Hangman.
Hangman.
Oh, okay.
The word was permission, though.
So it's related.
Okay.
Sure.
So, observable, but A equals position, and Hamiltonian is just kinetic energy, right? So, following the prescription for Heisenberg equation of motion, we need to practice this commutation. Right? So, instead of A, it is X. Instead of Hamiltonian, it's only kinetic energy, and we need to make commutation. Same as in your homework, we assume that there is a unknown function of X, but as soon as we are done with this algebraic procedure, we can remove it. So it's like pale or path blinking. There is and there is no. So it's just to help thinking. So the kinetic energy is this factor of constants and second derivative and x. And commutation, it means first minus second, first times second, second times first. Right? So second derivative and then position in the order as it was here, and then unknown function that we will move later. Minus position and second derivative. I hope on the next slide I have a little better calligraphy. Oh, previous years I was writing it down. Maybe let me know if it is not clear, and I'll happily write it online. So we do have two terms, first and second. And in the first term, there is a second derivative, which is subsequent occupation of the derivative to this product. So slowly but surely, first thing with the first. So we apply only the first derivative. And we practice derivative of a product. So first derivative of x and function unchanged, x unchanged, first derivative of function, right? Derivative of x over x is 1, right? And then we may want to practice the derivative once again to this unknown function plus x times derivative of function over x. So if we apply the first term as nothing, it's trivial, and for the second part, we practice the differentiation derivative of a product once again. So first derivative of x over x times first derivative of phi over x. X times second derivative over phi, over function, right? So 1 times derivative of function phi over x. And here it was derivative of function phi over x. So two similar terms. So we can remove this one and just put sign factor 2. And then we do have the last term that comes from the end of this commutation, of the minus. So x times second derivative of phi. So now I would like to look at one, two, three. Can we simplify it? Is there any similarity between the last two terms?
Just the opposite.
Right, so we can cancel them. And the result will be just 2 derivative over x over the function phi. So what we did now, We practiced if a stranger catches you in the store and tells you, "What are you doing in class?" You know, "I'm practicing operator algebra." Right? So it is what you did. So in this operation, we get this first term. And the function can be removed anytime. So the commutation of position and momentum will give the momentum square. Hamiltonian in position will get the first derivative, which is momentum. I was rushing. To use my old notes here, the same thing, right? Derivative twice, last term, apply product rule once, apply product rule twice, and then here we just keep the factor in front. Everything cancels except this one. So we have commutation of Hamiltonian and x, and here we can submerge h minus I h bar under this stuff to call it P, call it momentum. So if you use definition of momentum and play with factors in the right way, take one of the remove square and put h here. And if you want to have minus I here, we need to divide it by minus I. Then playing with factors, one is getting the following thing that is not mathematical, it can be interpreted. So change of time of expectation value of position is proportional to expectation value of momentum divided by mass. If it's not the most important thing, but you can maybe write it down and think a little about it. So change of position is value of momentum divided by mass. What is the definition of momentum? Just forget anything you heard in this class and look back at your common sense memories. And momentum divided by mass. So change of position equals velocity. You derived an important law, right? From advanced concepts. But it was not evident because on one hand, the quantum theory often behaves strangely. But in some limits, it provides answers that are very close or even equal to what we get from common sense from classical theories. So if we practice Heisenberg equation of motion application to position, we get this answer. Change in time of position is equals to velocity, or expectation value. Can we solve for this equation to find how position will change in time? Formally, no, because we do not know expectation value of momentum. So in some sense, we need to practice this equation once again, and instead of A, plug in momentum and check what will happen. It is quite easy. It's maybe additional 5-10 minutes, but now time is up, and I think it is enough today. Okay. Unless you catch me and So please take Wednesday morning easy, at least from 11 to 12, and try to show up in the lab at 5, especially the one who is reporting on the movies. But others may try as well. And on Friday, I hope airplane will bring me back.